When I start off our discussions of systems thinking, I usually always begin with a Slinky box and a Slinky because structure determines or shapes behavior. So if I were to hold the Slinky upside down, it would, of course, oscillate downward. If I were to hold the box down, what would happen? Well, it wouldn't oscillate, would it? And you might ask yourself, what caused the Slinky to behave that way? And many of you will probably answer gravity. But gravity did not change the way the box behaved, now did it? So this is an example of a video that I found that illustrates this dynamic better than I can, because not only does it illustrate how structure shapes behavior, but it also illustrates feedback, such as the signal that gravity sends. So in this case, we can see the Slinky is being held up. It's collapsing and falling down to the ground. So we have structural dynamics and we have Slinky dynamics. But this physicist is helping us understand which of these four options might happen when we drop the Slinky after we filmed it in slow motion. So you can see we have four examples here. It might close and drop. It might just drop. It might drop without closing or without changing, or it might pull together in the middle and then drop. So we're going to do a slow motion example while each of these people are being quizzed as to what they think. You might ask yourself, what do I predict will happen? Which of those four things might happen? So now we're going to look at this slow motion video. We're going to see exactly what happened. As you can see, the top of the Slinky met the bottom of the Slinky while the bottom of the Slinky stayed suspended, but then the Slinky fell. Why is that? What's going on here? The top of the Slinky is meeting the bottom of the Slinky. It's freaking everybody out. No one predicted that because it was happening so fast. But basically what's happening is that the structure of the Slinky is causing it to collapse and holding it in midair, because it's actually pulling, in a sense, from the top down, but gravity is holding the bottom of the Slinky in place. So what happens when we get this dynamic going on in space? Well, in space you can see the Slinky still oscillates and will wiggle in the absence of gravity. And the lesson here is that structure is still the dominant factor of the Slinky's behavior on Earth as well as in space. But when you take the Slinky and turn it loose, like these two astronauts did, you can see the Slinky met in the middle, both ends pulled towards each other. It vibrates the same way. So basically what's going on here is that gravity is not holding one end. Gravity is not at play here, but the structure of the Slinky in the absence of feedback, absence of the signal of gravity, is not the primary control. So on Earth we have two controls, one for gravity and one for structure. And then in space, structure is the primary dominant force with the feedback of the absence of gravity. So in this case, you can see, as these astronauts are illustrating, this Slinky will behave in all kinds of different ways than what we had anticipated before. And so the lesson I want you to take away from this as you begin to look at week two's systems diagrams is to think and to ask yourself, what is it about the structure of this system that I'm looking at that is shaping or that's dictating behavior? And then how is feedback exerting control on the way the system behaves? What's turning on the valves and off the valves? What's accelerating the flow? What is accelerating information? What pathways are exerting signals on the system that cause it to behave in a way that can be situationally different given changes in feedback, changes in structure, changes in different environments?